In quantum mechanics, all quantum states are vectors in a Hilbert space, and all elements of these vectors are complex numbers. The evolution of quantum states can be understood as transformations of the matrices corresponding to these states, which means performing matrix multiplication. Since most of our previous studies in linear algebra did not cover complex matrices, it can be helpful to convert complex vectors and matrices into equivalent real vectors and matrices for better understanding. To convert a complex vector representing a single quantum state into a real vector representation, we simply convert each complex number into a two-dimensional real vector, resulting in a four-dimensional real vector. All the quantum gates we will discuss later are matrices in Hilbert space, with all elements being complex numbers, where real elements should be understood as having an imaginary part of zero. In the section on complex numbers and linear algebra, we provided the matrix representation for complex numbers as operators. From this matrix, we can obtain the matrix representation for the imaginary unit I. Next, let's take the Pauli matrices we will introduce in detail later as an example and see how they should be transformed in the real vector space. To do this, we will use the concept of block matrices in linear algebra to convert each complex element in the matrix into its equivalent two-dimensional matrix. In this way, we can achieve equivalent conversions between complex matrices and real matrices.